Hello and welcome to the information presentation on electrical and computer engineering. My name is Liang Zhang. I'm an associate professor in the department, and I'm also the department director of undergraduate studies. So in this presentation, I'll give you a brief overview of electrical and computer engineering and explain what it does and what the program can offer you in its 4 years of studies. Apparently from our daily life, we know almost every application around us is impacted in some way by electrical engineering. And it's really difficult to imagine what life would look like if there were no electrical engineers or computer engineers. So what do engineers do really? And we know writers write, dancers dance, swimmers swim. So if we apply the same logic, engineers should engine. Now the word engine came from Latin, and the true meaning is to generate, to create, and to innovate. So the job of engineers is to create and design new things. So what do we know about ECE, electrical computer engineering? We know it must have something to do with electricity and all the applications that use electricity, like light bulbs, telephone, television, appliances, radar and sonar, transistors, computer, VLSI circuits, right? Computer chips, internet, cell phones, GPS, and so on and so forth. And I usually say, wherever you can think of there's electricity, there is electrical engineering. So what is the smallest form of electricity you can think of? And that's where the smallest form of EE, electrical engineering, starts. Now you can think of many things, but we probably can recognize that smallest form of electricity is from the atoms. You have protons, you have electrons. Both of them carry electrical charges. So that's where the EE starts, the smallest form of electrical engineering. Then what does the EE do in or at the atom level? Well, to answer the question, do you know what discovery led to Albert Einstein's Nobel Prize? Well, some of you may think of the theory of relativity, but no. Albert Einstein got his Nobel Prize for his theoretical explanation and foundation for something called the photoelectric effect. In physics, the photoelectric effect refers to the phenomenon that when you shine a certain amount of light, for instance, ultraviolet light, into a sheet of metals, the electrons will absorb the energy carried by the light and escape from the surface of the metal. And of course, the escaping of the electrons will form electrical current that can be utilized further on. This type of interaction of light and electricity is called optoelectric. And it's very common in electrical engineering because we want to take advantage of this particular phenomenon. And I can think of other similar phenomena that you can convert light to energy, particularly electricity. For instance, solar panels. For instance, the sensors on your digital cameras, and so on and so forth. Does it work the other way? Can you convert electricity to light? And of course we can, because when you enter a room, a dark room, switch on the light, and the room will become bright again. This is the form of converting electricity to light. But there are some other special forms of this conversion at the atom level. Now, if you design a stream of light careful enough, precise enough, and exact enough, it's possible to bring up the energy level of electrons to a design level. And because the electrons will like to go from higher energy level to lower energy level, when it makes this jump, it will release the same amount of same property of photons or light. And this can become a chain reaction, make the light even stronger. And this process is called light amplification by stimulated emission of radiation. Or if you take the acronym, it's the laser that we talk about in our daily life. Apparently, laser is a very important topic in electrical engineering. Now, on another topic, do you know who established the theoretical foundation of laser? You have seen the name before. It's Albert Einstein again. But of course, from Albert Einstein's perspective, although he made great theoretical contribution to both laser, meaning electricity to light, and photoelectric effect, meaning from light to electricity, he made the discovery but didn't really put them into new designs, new applications, so he's considered to be a physicist instead of an electrical engineer. Now let's move up from the atom level and look at electricity in a slightly larger scale. That will lead us to the nanotechnology and nanodevices area of electrical engineering. But what are they? Now, Apple recently released their A14 processor, which has 11.8 billion transistors. Now, we know how small a computer processor could be, and if you want to pack in this many transistors, each one of them are separated by a very small distance. That distance is only a few hundred copper atoms. And because at this small scale, a lot of general circuit rules do not apply anymore, and you have to take into account how these atoms will affect each other to transmit signals, electricities, and so on and so forth. This brings us a very important research field in electrical engineering. That is what nanotechnology and nano devices try to tackle. Of course, in addition to computer processors, we have solid-state drives, which goes from a few gigabytes in the previous years. Now you can go to terabytes of solid-state drives these days with relatively low price, and these were made possible only by the advancement in this nanotechnology and nano devices field. Okay, and there's also storage devices, computer memories, and so on and so forth. Those semiconductor technologies all contribute to this nanotechnology, nano devices area. Another important field of electrical engineering is power, because this is where most of us get to use electricity in our daily life. And the first thing is, where does the power come from? It comes from generators, from different sources, right? From gas powered generators that we usually use in power outages, power plants, some renewable energy sources, and of course, the opposite of this generator will be electric machines, right? When you convert other type of energy to electricity, that's your generator. When you do the opposite from electricity to kinetic energy, that's the electric machine, the motors and drives. And of course, when you generate the electricity, you have to transmit them. There are a number of things that need to be considered, right? How much loss of energy, electricity will happen during this transmission. If a certain part of area is suffering from power outages, for instance, because of inclement weathers, how will this impact the overall grid that will possibly propagate to other areas? And can you isolate and identify that particular area that has this fault and quickly recover the electricity supply to that area? Those are the important problems that we'll study and learn and also research in this power systems area. And of course, when you generate power, sometimes when you have surplus, you want to store them. Okay? So battery technology is another type, another direction, an area of power systems that in our department we learn, we have courses and we have faculty members doing research in that particular area. One last thing is what we call power electronics. Power electronics, the commonly used power electronics will be these power supplies that we use for computers, for cell phones, that are used to convert one type of electricity to another type of electricity. For instance, to alternate current, that's when you plug in your wall into your wall outlet, that's your AC or alternate current. And when you plug in your USB-C interface or lightning port to your phone, right? That's what we call a DC direct current. These two types of electricity also have different powers and voltage levels, right? When you have the AC is 11 volt, 110 volts, And when you have the USB-C, right, it could be 5 volts, 10 volts, and so on and so forth. We have to take into account of those factors and make these devices possible and capable of converting from one type of electricity to another. And of course, we want to make this type of devices lighter, but also maintain enough safety so that it won't get overheated and so on and so forth. Right? And again, we have faculty members teaching courses and doing research in this area as well. And of course, the most commonly seen applications of electrical engineering will be the electronics. They include our computers, personal devices, and also the circuit board within those devices. Those are the important things that we need to figure out. For instance, how you can ultimately arrange all these components on this small circuit board so that you can save as much space as possible, but still deliver enough power and also maintain, of course, safety in those devices. Another area in electrical engineering is what we call systems, which also covers a wide range of applications. For instance, we have control. Like this drone, when you command it to go from point A to point B, right? How you make sure that this device will follow your command in the optimal manner. Of course, you have to adjust the voltage current supplied to these propellers during the whole course of this task to make sure it doesn't fall to the ground, doesn't hit an obstacle, and so forth. We have communication. We're going from 4G to 5G, right? Now, how you design the software and hardware so that this new communication protocol will satisfy the throughput, latency, and other requirements under various type of constraints and environments. Robotics is enjoying a lot of success and advancement in recent years, and the UConn is now exploring the possibility to create a curriculum, a program in robotics engineering as well. And we have a number of faculty members in our department doing research and teaching courses in the area of robotics. Robots are being used not only in industry environment these days, it's used in healthcare environment, service, and other areas as well. So it's a very promising field that a lot of electrical engineers are contributing to. And also we have estimation, right? When you receive signals, for instance, from radar or sonar, how can you estimate the exact location of the object you're trying to detect? Right? This is not only in this aerospace type of field or applications, can also be used in medical field as well. How you can track a certain cells, for instance, cancer cell. Signal processing, right? This is the image of the black hole, the first image of black hole. Right? The leading scientist of this project actually got her bachelor degree in electrical engineering from University of Michigan. And signal processing refers to the field where you gather data and apply, model-based method, a lot of math involved, of course, to eventually extract the information you'd like to see. For instance, using a whole bunch of data collected from various areas, we're able to create this image of the black hole. And also systems, when we deal with signals, we have collaborations with other fields, for instance, biomedical engineering. Now, this image, the last image, shows a cochlear implant, where this device is actually directly connected to the nerves of a person, such that they can enhance and make it possible for the person to be able to hear things. Of course, now there are electricity involved, so you must be electrical engineering involved in this studies, but also because you're dealing with a person with biological mechanisms. BME, biomedical engineers are also involved. Sometimes medical doctors are also involved as a collaborative effort to make things happen. Now, computer engineering is a joint degree between electrical engineering, ECE, and computer science and engineering department. It also tackles a wide range of problems, but from the ECE side, we're mostly view, computers, they are electrical devices as well. So a lot of electricity is going on. For instance, when you have this USB-C port, right? It has a number of pins involved, and each of the pins must be transmitting certain electricity or electrical signals, right? How we design the mechanism, how we design the protocols there, they belong to the field of computer engineering. There are other things, for instance, when you have computer chips, right? How you can make sure that this computer chip or this processor is not a counterfeit, right? How you can ensure the security or the safety of this computer chips, the algorithm design, the architecture, and so on and so forth. All of those questions belong to the field of computer engineering. Now, our department offers currently 3 majors. EE is the main one. Computer engineering, as I mentioned, is a joint program degree with computer science and engineering department. We have also an engineering physics major, right? That's jointly between ECE, ME, material science, and also Department of Physics. We have 2 related minors that students from other departments and programs can choose to explore. One is the nanotechnology. I also mentioned what nanotechnology is about, and then the electronics and systems. Now here are some students and faculty data in this semester. We have about 400 undergraduate students involved, all 3 majors. Graduate students about 120. In the last academic year, we conferred 86 EE major bachelor degrees and 11 computer engineering department degrees. Graduate students, we graduated 6 master students and 11 PhD students in the last academic year. We have 27 faculty members, and we have the student-faculty ratio is about 14, which is quite good within the School of Engineering in our university. And also our faculty members contribute to all different areas of EEs and computer engineering, as we can see from this distribution chart. Now, as far as the curriculum is concerned, our majors EE and computer engineering curricula requires 126 credit hours to graduate. Right, the first 2 years usually is commonly among all engineering disciplines. Right, you take a broad range of math, physics, chemistry, and other courses. The last 2 years, senior and junior years for the upperclassmen, you would take more focused areas in the area of EE or computer engineering, and you have to take the lab courses and finally the senior design in usually the last 2 semesters. So the curriculum sheets can be accessible through our department website. Now here is just a screenshot of for the majors. For instance, if you look at EE, in the sophomore year, you start your first EE course, ECE 2001. That's the electrical circuit. That's the first and most fundamental course in EE. Right, and then in the second semester of your sophomore year, sometimes either in the summer or in your junior year, you take more AE courses like 3101 Signals and Systems, 3201 Electrical Circuit, which we also call Circuit 2. So it's advanced circuit class, the second circuit course, in addition, following 2001. And then starting junior and senior year, you will see you need to take 4 restricted electives. So the goal is to expose students to 4 different directions in EE: communication, power, nanotechnology, and systems, and so on. And then senior year, you're going to take your senior design to course sequence 4901, 4902. You're required to take 4 professional requirement courses, and 2 of them must from ECE, and the other 2 came from other STEM fields, but it must be 3,000 levels or higher. And you can see you also require you to take 2 design labs so that you not only get theoretical training, you'll be able to get more hands-on experience in the labs. For computer engineering curriculum, it's similar, but now you can see you're also required to take a few CSE courses along the way, like microprocessor, programming, computer architecture, so they can build a nice understanding of the computer engineering as well. Engineering physics, now because it's the joint program with physics, you're now going to take more physics class as well, as you can see from the curriculum. Electricity, magnetism, um, optical engineering, um, quantum mechanics, um, optoelectric devices, and so on. Okay. And as you can observe from this curriculum, right, the atom level and nano level electrical engineering are sort of the focus in the engineering physics curriculum major. Now we have good opportunity for associated minors and co-op opportunities, right? We have, in our curriculum, you typically will take some math courses, um, so that will make it possible for some students to go ahead and to take some minors in math, for instance, information technology, biomedical engineering, physics, nanotechnology, and so on. We have students taking co-op and intern during the process of their 4-year study here. Um, in the past, students are taking advantage of the Eurotech and other study abroad opportunities. We have very good and active student chapters. They are nationally recognized and awarded student chapters in our department. Um, Senior design is a year-long adventure, 2-semester sequence. Our department has been sponsored by a number of big name companies like Otis, EDC, which is now Collins Aerospace, MITRE, Sikorsky, Electric Boat. Some of them are local, some of them are also national companies. In the last day of the spring semester, we usually hold this design day in Gampo. Um, Under this COVID situation, the last year we have been holding this demo day virtually, and then we have students demonstrating their project using videos and the online presentations there, which is exciting experience for the senior students to eventually apply what they have learned in their program to apply it to some real and exciting applications. And in addition to normal coursework, uh, our faculty members are open to work with students in independent studies, um, undergraduate research, and many of the students can take advantage of the graduate course credit recognition policy and eventually get a head start for their professional career or go to the graduate school, no matter is it at UConn or in other universities. Now, as far as career is concerned, the compensation for electrical engineers has been, among the top ones throughout the years, and the demand for AEs have also been strong in the past few years as well, especially with the new wave of this Industry 4.0 with AIs. Although computer engineers are in great demand, everything has to put into devices um, which are powered by electricity, of course. So the AEs are still in very strong demand. The mean starting salary, as you can see, computer and AE are roughly head to head. And it has been among the highest among all engineering disciplines. Um, this is from their after they graduate from with their bachelor degree. So our department is housed in the ITE building, Information Technology Engineering building, which was completed in 2003. Of course, because of the COVID, we're not able to. The faculty members are not able to do much work this period of time in the IT building, but we'll be holding some virtual out of classroom presentations, hopefully to get you more familiar with our department. And welcome you to feel free to go onto our website, look at our curriculum, look at what we offer, look at what faculty members are doing with the research and so on. And if you have any question about the department, you can feel free to get in touch with me. I'll be happy to answer all your questions. Well, thank you and have a good day.